He has got many awards and achievements. He got his Alexander Humboldt Fellowship in 1999 from 2000, Fellow of National Academy of Sciences, Ahmedabad, Associate Editor of Separation Science and Technology, and one of the editors of Vedic Acta. Dr. Mahapatra has over 400 publications in peer-reviewed international journals with over 8,000 citations. So, with this brief introduction, I invite Dr. P.K. Mahapatra to deliver his lecture.
Thank you, Dr. Chaudhary, for your kind introduction. At the outset, I thank the organizers for giving me this opportunity to speak at this August gathering. The topic of my presentation is selective dissolution of metal oxides in room temperature ionic liquids, the new strategy in separation science. The morning we had this lecture by Professor Ken Derwinski of UNLV, where he was talking about from the oxides you are converting by the fluorocompounds. Now here I will be talking about these oxides, how the metals can be removed, recovered by using room temperature ionic liquids. This is the outline of my lecture. First I will give a brief introduction of the nuclear fuel cycle, then the aqueous, non-aqueous reprocessing, room temperature ionic liquids, dissolution in ionic liquids, dissolution using functionalized ionic liquids, and some of the case studies which is carried out in our laboratory, BARC, that is dissolution of UO3 by DEFA in ionic liquid. DEFA is di-2-ethyl phosphoric acid, it's a very commonly used extractant. Then dissolution of EU2O3 by HTTA is another commonly used extractant, that is phenol trifluoroaceton in ionic liquid, and conclusions. Now first coming to the nuclear fuel cycle. Here I have given a pictorial presentation of this nuclear fuel cycle. You have this mining and milling and then enrichment, fuel fabrication, going to the nuclear reactors. And after this operation in the nuclear reactor, the spent fuel is kept for storage for a number of years, maybe 5 to 10 years, then fuel reprocessing, vitrification, and then finally it goes to the deep geological repository. Now this is the general practice in a closed fuel cycle. Those who are going for this open fuel cycle or once through fuel cycle, of course this is not the strategy for them. After this spent nuclear fuel is coming from there without reprocessing, you can keep it for storage and then deep geological repository. Now once you are coming for this fuel reprocessing, the most commonly adopted method worldwide is the Purex process, where you have this chopping of this fuel pins, then dissolution, and this Purex process is there where you are separating the uranium and plutonium using 30% TBP, and the fission products are separated along with the activation products, goes to the waste of the raffinate. In some cases, of course, people are trying to have this separate some of the important fission products like cesium-137, strontium-90, and ruthenium-106, like that. Some of these fission products can be separated from this Purex raffinate which is coming out, and also there is a strategy called actinide partitioning, which is part of this P and T strategy which I mentioned here, where you can separate the long-lived actinides and then it is transmuted in a high flux reactor or in the ADSS system. Coming to this aqueous reprocessing, you know this Purex process is the backbone of the nuclear reprocessing, and it is widely used worldwide for the spent nuclear fuel reprocessing. This technology is well developed. The major advantage of the Purex process is that this is a very simple process where you have very high decontamination factors from fission products is obtained. These are the two chemical reactions which are there for the plutonium as well as uranium recovery. This M is Pu here. So you have the Pu 4+, 4 nitrate, 2 TBP in the organic phase, gives the extracted species as M, that is PuNO3 4 times 2 TBP. And for uranium, you have this UO2 2+, 2NO3, 2 TBP in the organic phase, giving this UO2NO3 twice, 2 TBP in the organic phase. So these are the profiles, as you know very well. This is where the plutonium extraction is somewhat lower than that of the uranium extraction. In case of the Purex process, you get a peak around maybe 6 to 7 molar nitric acid concentration, and then there is decrease in the extraction of uranium as well as plutonium because of factors like the anionic complexes for plutonium. In case of plutonium, that is why you see the more decrease in, you are seeing. The other factor, common factor for both uranium as well as plutonium, the TBP forms a adduct with the nitric acid. Now, in spite of the lot of advantages of this Purex process, there are some disadvantages, like the cooling of this spent nuclear fuel is required for a few years. Otherwise, there will be definitely a problem because of the solvent degradation can be there because of the high radioactivity which is there in the spent nuclear fuel. And you deal with large volumes of organic solvents. There are proliferation concerns because you are going to get pure plutonium in this case. And there are solubility issues also with, like the third phase formation. If you have the fast reactor spent fuel reprocessing, then of course the plutonium concentration is much more there. So you have third phase concerns. And also there are some problems generally with the solvent extraction processes, like phase entrainment, and also the other problems are there, which are there in case of the Purex process. But still, we are continuing with the Purex process. There are of course attempts by other groups. For the aqueous reprocessing, they have suggested the amide-based extractants. But there are also the large volume of research has been taken place in different countries about something called the pyrochemical processing. Of course, there we are talking about the fuels which are different than whatever we are using in the normal reactors, mostly for the metallic fuels, or nitride, carbide, or even cermet type of fuels. So this type of cases where the pyrochemical processing, the technology is well developed in Argonne National Laboratory. A lot of work has been carried out in the pyrochemical processing. In the Russia also there are a lot of work has been carried out. This RIAR Russia, a lot of work has been carried out on this pyrochemical processing of the spent nuclear fuel. And in ITU Germany, and TRIP Japan, and ICAR India also there are a lot of work carried out in the pyrochemical process, reprocessing. The common feature is that it uses the molten salts like lithium chloride, potassium chloride. Using this sodium aluminum, this here I have taken this aluminum, solid aluminum. This aluminum is used in the case of this ITU Germany. And I think this RIA Russia, they are using graphite cathodes. It's a very standard methodology available. But it is not presently used, this pyrochemical processing. It is recommended for the Gen 4 reactors with the metallic fuels. Now, in this process, the fuel is electrochemically dissolved in the carrier melt. And in this process, the fuel is in carrier melt forming a mixture of actinide as well as the fission product ions, and all actinides are selectively recovered from the melt by electrodeposition. As I have shown here, you have this anode and this cathode where you have this actinide aluminum alloys formed in case of this ITU Germany process, which I have given this schematic for that. And this advantage is that it is a little cooling is required for the spent nuclear fuel. So you can have it actually near the reactor facility, and without much cooling actually this spent nuclear fuel can be processed. Does not need carbon hydrogen based solvents, which is there for the aqueous reprocessing because of the criticality issues, and also there can be radiolytic degradation of these solvents because of high dose which is there in case of this spent nuclear fuel. There is a possibility of on-site reprocessing at the reactor site, and it can address the non-proliferation issues because along with plutonium you can also have the other actinides deposited. So this is proliferation resistant. And the disadvantage is that the operation is carried out at a very high temperature because of this melts of the lithium chloride and potassium chloride. It forms at maybe greater than 700 degrees Celsius. So naturally the question comes, can we have a melt or the ionic medium operating at room temperature? the last 2 decades or so, people are working on room temperature ionic liquid. This is ionic medium. Whether it can be a really good substitute for the melt, which were used in the lithium chloride and potassium chloride. Now, what are these room temperature ionic liquids? So you have basically this ionic bond. We know that it is usually stronger than the van der Waals forces between the molecules of ordinary liquids, like the molecular solvents. And common salts tend to melt at higher temperature than the other solid molecules. You can see here at the room temperature here it is around 25 degrees. So thermometer is shown here. Sodium chloride is a solid, whereas this ionic liquid, whatever is shown here, it's a butyl methyl imidazolium NTF2. This is one very commonly used ionic liquid. You see that ionic liquid is liquid at room temperature, whereas sodium chloride is solid. 1914, that was the first report on the synthesis of ionic liquid. This is the ethyl ammonium nitrate. So this was reported by Walden and his research group. 1992, Wilkes and Javatko obtained ionic liquids with a neutral weakly coordinating anions such as the NTF2, PF6-, BF4-, etc. So in between 1914 and 1992 also there are several ionic liquids people have used, but they were not used particularly for this type of applications like what we see these days, these ionic liquids, that is the extraction or catalytic activities. There are some aluminum chloride based ionic liquids were used previously. Now, of course, there are the suggestion that these room temperature ionic liquids are green alternatives to the volatile organic compounds used in the solvent extraction. But this green alternative, when I am talking, that some people say that it is a green alternative, but there are good number of people opposing that the ionic liquids are really not green, because there are so many issues we have not settled it to call it as a green diluent. There are, of course, that good number of suggestions that these ionic liquids can be used as a diluent in the nuclear fuel reprocessing. There was a good review by Seng Dai and his co-workers in 2012, published in Chemical Reviews, where he has suggested that these ionic liquids as solvents for the fuel reprocessing. However, it is still a lot of work has to be done actually with ionic liquids to suggest that they are really fit for the nuclear fuel reprocessing. The major advantage of the ionic liquids, you can have a lot of these cationic parts in the ionic liquid, and these anionic parts as shown here have of course represented only limited number of anions and cations. But by combining these cations and anions, you can have a very large number of ionic liquids. Maybe several thousands of the ionic liquids can be prepared, where you can combine this cationic part as well as the anionic part of shown here. Now, coming to the dissolution in ionic liquids, of course, there are a lot of studies have been carried out where ionic liquids are used in the solvent extraction. In the late 1990s, there were reports from Robin Rogers' group where he has used the ionic liquids, which are hydrophobic ionic liquid, for the solvent extraction. And there are a lot of encouraging results in the solvent extraction studies using ionic liquids. I'll give one example. For example, this strontium extraction by a normal molecular solvent using a crown ether, you get a distribution ratio of strontium maybe something like 10-20 you can get. But you take the crown ether in an ionic liquid and you can get the distribution ratio of strontium several thousands. So that was very promising actually, which was published by Professor Robin Rogers' group. That is, ionic liquids are really very, very efficient extractants, diluents, where you can have your extractant make the solution or make the solvent, which can be very, very efficient in extracting the metals from the aqueous medium. But that is one part of the story. I am not discussing that in this lecture. What I wanted to know that whether ionic liquids can be really true alternative to the pyrochemical processing, that is the melts what I have talked about, with sodium chloride, potassium chloride type of systems. So for that, what we need to do is that this metal oxide we can dissolve in the ionic liquids, and this is a very, very challenging topic because the ions of ionic liquids are very weakly coordinated. As I have shown, most of these ions are weakly coordinated, And these chloride-based ionic liquids are better, but are corrosive and moisture sensitive. This is another problem. Ionic liquids, generally you have this viscous, the viscosities are high, so the viscous medium means mass transfer is poor. And these functionalized ionic liquids are found to be very effective in metal oxide dissolution. So now these are some of the points I have mentioned here, which are actually should be considering while carrying out the dissolution in the ionic liquid. First is that you should have a free chloride ion in the ionic liquid. If you have a free chloride ion, then the dissolution is facilitated. If you have free mineral acid in ionic liquid, it helps in the dissolution of the metal ion. If you have presence of the acidic hydrogen atom, that also helps in the metal oxide dissolution. If you have acidic expectants in the ionic liquid, it helps in extraction. And one important parameter is the lattice energy of the materials. When we are talking about the different oxides, so depending on the lattice energy of these oxides, so the dissolution can be different. And another very important factor is the water content of the ionic liquid, the structure of the oxide and the effect of the temperature. Coming to the water content, as shown here on figure, you see that if it is a particular metal oxide, I have taken this metal oxide leaching weight percent, and the time is given in hours. You can see up to 100 hours this data is presented. And if it is a water-free ionic liquid, then you see that it is very, very poor. Even after 100 hours, you get less than 20% leaching. But if you start adding water to the ionic liquid, 5-8% water, you find that within 20 hours, you get close to 100% dissolution of the metal oxide. So this is actually one of the strategies that to have is water in the ionic liquid. And ionic liquids as a solvent, some of the ionic liquids which are commonly used in the laboratory, they have good solubility of water, can have maybe 1 to 1.5% water can be there dissolved in the ionic liquid, so that helps in the metal oxide dissolution. Now, coming to the spent fuel reprocessing, as I was suggesting, so you can have the spent fuel dismantlement, oxidative dissolution, and then recovery of UO2 and PuO2 mixed oxide by the electrochemical reduction. So you recover the UO2 and PuO2, and the fission products can be separated this way. So we have a review article last year published in Separation Science and Technology, where we have discussed in detail the various factors which are actually deciding the dissolution of metal oxides in ionic liquids. Now, as I have mentioned, these are the task-specific ionic liquids. These are one of the early reports, maybe around 2006 or so. There is a report of the metal oxide dissolution by a task-specific ionic liquid. When I talk a task-specific ionic liquid, that means you do not need an extractant in the ionic liquid. So this H-bet TF2N is the betaine. Actually, this is the structure of the betaine, and this is the NTF2 or the TF2N anion. So this itself can act as a ligand, or it can do the dissolution because it is having a carboxylic group attached here, and this can form a complex with the metal ion. So this 2006, this work was published by Noteman and co-workers in Journal of Physical Chemistry. What they have shown is that this ionic liquid forms a complex with the metal ion, and the presence of water facilitates the dissolution. This is very, very important, the presence of water. They have carried out the dissolution of copper oxide, and they have shown that even in case of the absence of water also, this dissolution of copper oxide was possible. But this is an exception. Oxides of iron, cobalt and aluminum were insoluble in presence or absence of water with this particular task-specific ionic liquid. And the solution of this ionic liquid, this task-specific ionic liquid, in other ionic liquids were used because this H-bet TF2N is a solid at room temperature. So you can make a solution with the room temperature ionic liquid and make a solution which has been used for the dissolution. The mechanism of binding, as is shown here, you get this particular betaine ion here, betainium ion, and this forms a complex. You have two of these cationic part, which is of the ionic liquid, which is binding because of this losing a proton from the carboxylate group, and with this metal, this oxygen of the metal, it forms a water, water molecule, and that is how basically this dissolution is possible. This was also, there is another article by this Richter and group in 2019 where they have proposed this mechanism, and they have also carried out this dissolution of large number of metal oxides. It's a good reference you can see on this ionic liquid dissolution of metal oxides using ionic liquids. Another report was there in 2016 by Bruce Moyer's group, it's Vaniga Sekara and Bruce Moyer. So they are amide-based class-specific ionic liquids for the UO3 dissolution they have reported. So basically they started with another nuclear fuel has the UO2. So what they do is, this UO2, they try to oxidize by voloxidation and they convert it to UO3 and then carry out this dissolution. This is the class-specific ionic liquid where it has an amide group, and then after this is dissolution, they do the electrochemical deposition to UO2, and they say that this net reaction is UO2 to UO2 conversion, and UO2 gets converted first to UO3, and they carry out the UO3 dissolution in the ionic liquid, in the class-specific ionic liquid, and then subsequently this ionic liquid containing the UO3, uranium-6 is then electrodeposited. So these are the reactions given in the anode and as well as the cathode. And this they have proven by spectrophotometry. Very recently, there was a group from the report from the Chinese group in 2019 published in Inorganic Chemistry, where again they have taken this betaine-based class-specific ionic liquid, and they have suggested that the separation of fission products by an ionic liquid, and they said that this can be used for again nuclear fuel recycling, reprocessing. So what they have done is the selective dissolution of the lanthanide oxides as well as some of the fission products. They have seen that it is very easily dissolved, and this UO2 matrix and the minor actinides, they are left behind in the spent nuclear fuel and accomplishing the actinides recovery as a group. That means if it is actinides are there in the tetravalent state like UO2 or americium oxide, that is AMO2, then it is not dissolved by this class-specific ionic liquid, whereas the fission products are dissolved. So that is how they say that it can be selective separation of these fission products from these actinides. So they have shown here, there is a scheme they have presented where they have shown that this uranium, thorium, neptunium, plutonium, americium, cerium and zirconium in the solid, whereas yttrium, lanthanum, praseodymium, neodymium, samarium, europium, etc., all the rare earths as well as cadmium, strontium and barium, they will be in the solution. So this is how you can have a selective dissolution and have the separation, which is having possible application in the nuclear fuel recycling. So that they have mentioned that this big difference in the dissolution provides a novel separation approach to spent nuclear fuel recycling and may open new perspectives for the spent nuclear fuel reprocessing. Now, after this is the background I have given, what people have already carried out the studies. Now, I will give some of the studies which we have carried out at Radiochemistry Division BARC. So, the two case studies I will be discussing. The first one is UO3 dissolution by DEPA, that is di2-ethyl phosphoric acid in ionic liquid. So, this is the structure of DEPA and it exists as a dimeric form. You see, I have shown here. So, what we do is we have taken this powder UO3 and then put it in a magnetic spiral in a flask, and then we add this ionic liquid here. In this case, we have taken 1-octyl-3-methyl-imidazolium, NTF2. This is the ionic liquid we have taken. Why? Because this DEPA doesn't have good solubility in the butyl-methyl-imidazolium, which many people have been using for the ionic liquid. So butyl-methyl-imidazolium doesn't have good solubility, so we have taken octyl-methyl-imidazolium, which has reasonably good solubility of HDSP. And then we have added this, we have started stirring it, and we start for quite some time, maybe around 24 hours we have stirred it, and then we have transferred to a centrifuge tube. And then after centrifugation for 15 minutes, we have seen that this dissolved phase splits into two phases. One is the upper phase and another the lower phase. And the upper phase actually is the concentrate of the uranium DEPA complex, whereas the lower phase is the ionic liquid. So basically you are having a pre-concentration. First you are having a dissolution and then you have a pre-concentration of the uranium in this complex with the DEPA dimer. And that is how you get a very promising result, because instead of having the entire volume of the ionic liquid, we are having basically in a very small volume of this ionic liquid in the upper phase. And this was published in Inorganic Chemistry in 2021. Then we have tried to characterize this extract. The upper phase we have done by this FTIR analysis we have carried out. You see the upper phase spectra is shown here and the HDSP spectra is shown here. See that there is a lot of similarity between the spectra of HDSP and the upper phase, and the lower phase spectra as well as the C8 beam NTF2, that is the just ionic liquid, that spectra both we have shown, and you see a lot of similarity between the C8 beam NTF2 as well as the lower phase. So suggesting that this HDSP along with the uranium, it has gone to the upper phase and only the ionic liquid they are present in the lower phase. So these also we have tried to characterize by the UV visible spectrophotometry. So what we have shown here, once we have the dissolved sample of this uranium trioxide UO3 in the ionic liquid, that spectra is shown in the red part of this UV spectra, you see that. And the upper phase we have taken the spectra, and you see that there is a very good match suggesting that the dissolved sample what we have before the phase splitting, the dissolved sample, that is the uranium complex with the DEPA as well as the upper phase, they are more or less matching, suggesting that the same nature of this upper phase as well as the dissolved sample. And we have taken this complex uranium HDSP complex and also this uranium in C4 beam NTF2, that we have seen this complex, when this uranium in C8 beam NTF2 means this we have taken just salt of uranium, that is C8 UO2 NTF2 twice. This salt we have done. We have taken uranium and dissolved in NTF2, HNTF2. So that complex is UO2 NTF2 twice, which we dissolved in C8 beam NTF2, and that spectra is shown here. And if you have this DEPA complex, then this is the black spectra is corresponding to that. So that means this red line where uranium is not complex, so there is, you see a shift is there because of the complexation with the phosphoryl group of the DEPA. Now we have taken this, also we wanted to know whether this nature of this complex, what we do by this normal solvent extraction. So we carried out the solvent extraction of uranium, taking DEPA, and we have taken this whatever dissolution we have done by this ionic liquid DEPA mixture, that also is red spectra is that, and this is the solvent extraction spectra. You see that there is almost a good match with that. So suggesting that the nature of the complex in the organic extraction by the normal aqueous biphasic extraction, the same thing we have seen along with the as we got with the dissolution. So suggesting that the species extracted is the same. Now this here I have included this extract whatever we have taken, that we have tried to carry out the electrodeposition, and it is possible to get uranium oxide from this extract. So that is how the cycle is completed. You start with uranium oxide and then you dissolve it, then you try to get it by electrodeposition. So you started with uranium oxide and end up with uranium oxide. The only problem here is I wanted to mention that UO2 was not possible to dissolve. When you started taking this instead of UO3, so we are not able to dissolve UO2 in this method. Now the major difference between our method and the previously reported methods, because they were taking all carboxylate based task specific ionic liquids, whereas we have taken an ionic liquid containing a extractant or a ligand, which people have not attempted before. So that is what we have taken. So we basically wanted to form a complex, and the hydrogen ion which is generated because of the complex formation, that is releasing some amount of water molecule, and that is how the metal ion dissolution was possible. The second case study what we have carried out is a selective lanthanide dissolution in case of the HCTA. Here we have taken phenyl trifluoroacetone in a ionic liquid, and this ionic liquid in this case is the butyl derivative instead of the octyl derivative which we have taken in the previous case. we have taken the butyl derivative. So again we have taken one acidic extractant, this HTTA. Now why we are taking acidic extractant? Because we wanted to form a complex and the proton is which is generated that can give some water molecules, and that is how this dissolution is facilitated. So we have carried out this study actually for the lanthanide actinide separation. As many of you may be knowing, this partitioning and transmutation strategy, one of the key steps is the separation of the trivalent actinides from the trivalent lanthanides because of the large neutron accretion cross section of the trivalent lanthanides, and they act as the neutron poisons. So because of that, this trivalent actinide, trivalent lanthanide becomes very important in the aqueous processing, and there is a large volume of research is going on in the European Union in this, and also in the BARC also there is a lot of work is going on in the lanthanide actinide separation. So we wanted to see whether the dissolution, selective dissolution, whether it can be done. So as I have already mentioned in the previous one of the previous slides, that the structure of this metal oxide is very important. So americium dioxide, which is the oxide of americium, has a fluoride structure, whereas this europium sesquicide, it has a cubic or monoclinic structure. Now you see this lattice energy of this americium oxide is 10,540 kilojoules per mole, whereas that for europium oxide is 6469 kilojoules per mole. As a thumb rule, if the lattice energy is greater than 10,000 kilojoules per mole, then this dissolution becomes difficult. So this is what we have exploited. 5 minutes? 30 minutes over, okay. I'll take 2 more minutes. So that is how if you take this americium oxide, you can say based on this lattice energy, you can predict that americium oxide is very difficult to dissolve. Same also was seen as the previous case, uranium dioxide was not very easy to dissolve with DEPA. But if you have this sq oxide, they have a much lower lattice energy, that is how their dissolution is facile. This was also reported by the Chinese group, which was published paper in Inorganic Chemistry in 2019. They have also shown that a lot of these lanthanides are soluble, but they have taken the butane-based task-specific ionic liquid. TTA, we have carried out these studies, and the structural difference between americium oxide and europium oxide we have exploited in this work, which was published again this year actually. Early this year it was published in Inorganic Chemistry. So I give the scheme of presentation, scheme of dissolution here. So we have a mixture of americium oxide and europium oxide, and we put it in again a flask, and then we start putting a magnetic stirrer. And after stirring, we can have a filtration. So then we find that this europium oxide actually is dissolved and the americium oxide is not. So this is basically the schematic of this separation. Now how it is taking place? So because phenyl trifluoroacetone or TTA is a acidic extractant, it exists in a keto as well as the enol form. So the complex formation basically is taking place by the enol form of the TTA. So that is why if you have a keto form of the TTA, slowly it gets converted to the enol form, and then this particular form is actually forming a complex with the metal oxide. So this is the mechanism we have given here, 3 TTA half M2O3 forming this MTTA thrice 1.5 water, and these water molecules are released. This also helps in the dissolution. So these are, I have shown here the XRD patterns of this sq oxide of europium and americium, and also I have shown that for the UO3 and UO2. So as you can see here that this TTA has a very strong binding capacity, the log beta value being 17.8 with the trivalent F cations in the room temperature ionic liquids. In ionic liquids, basically the complex formation constants are much higher than what we see in the other solvents. So what we have not shown in case of the, generally it is reported that this temperature has a very good, very important role in case of the dissolution. So if you have this different temperatures, carry out the studies at 25 degrees, 45 degrees and 65 degrees, we find that there is not very significant difference. So if you see minutely, there may be little increase in the dissolution rate, but not much very significant effect was not seen in this case. And also we have seen that if you have this, keep this, carry out this extraction, dissolution with TTA, based ionic liquid solvent. Suppose you prepare the solvent and carry out the dissolution the first day itself, then it is very slow. You prepare the TTA and ionic liquid mixture and keep it for 7 days, and the 8th day you carry out the dissolution, you find that it is faster. And if you keep the the solvent for 15 days and then you do the dissolution, you find it is very fast. So this suggests that this TTA based solvent, whatever you are keeping, it is picking up moisture, and that is how, because the water molecule basically helps in the dissolution of this metal oxide. So that is the difference between the dry ionic liquid and the wet ionic liquid. So we have carried out the systematic study by allowing this solvent to be equilibrated with water, and then whatever amount of water which has taken up, with that we have carried out the studies. And we have seen that only 15 minutes are required for getting the quantitative dissolution. That I will come in the next slide. So what we have concluded is that a poor europium oxide dissolution in dry ionic liquid is not changing even at the higher temperature, as I have shown here, and the complete dissolution of europium is achieved in less than 30 minutes if you have the wet ionic liquid. This is what I have shown here. This is the wet ionic liquid. So you find that even 30 minutes is good enough for getting 100% dissolution. And also aging helps in dissolution. As I have shown here, if you keep the solvent for some time, then the dissolution becomes easier. So this we have tried to prove it by carrying out some FTIR studies. See that this, just if you take the ionic liquid, this green line, you don't find much of this water molecules present there. If you have this wet ionic liquid, then you find a lot of water. Dry ionic liquid, AZ, you have some amount of water. And dry TTA ionic liquid, if you have, this is again not having water. So that is basically, if you have water in the ionic liquid based solvent, then this helps in actually basically the transformation of the keto form to the enol form, and that is how this enol form is important in the binding with the metal ions. So that is how the enol form, if it is formed by some means, that means by putting water molecules in the solvent, then it basically does the dissolution fast. Now, what we have done is we have seen that this heating also, there is also this oxide, suppose we heat at a particular temperature, we have carried out the heating at 600 degrees, then we have seen also that it helps in better separation. So see this magenta line here, this is for the americium dioxide. The dissolution goes around 20% if it is around 6 hours or so. But if this americium oxide dioxide is heated at 600 degrees, then you find almost more dissolution. So this is one of the very important findings, that you have to heat it at around 600 degrees. So you find that this americium dissolution is not there. Whereas europium, whether you heat or you do not heat, there is no effect, and you get nearly 100% dissolution in around maybe 1 hour or so time. So suggesting that you can do a separation, very clean separation of americium from europium if you are doing this heating of these oxides. So these kinetic studies we have done, and as you can see here is americium dioxide and europium oxide mixture. So it's almost 100% dissolution of europium, and americium is maybe around 0.1% or so. So this suggests that the dissolution of americium oxide, and same also we have seen with uranium dioxide, is found to be very, very poor. So uranium dioxide was taken for the comparison purpose because the spent nuclear fuel contains uranium dioxide as a major component, and the quantitative dissolution of this europium oxide is achieved from the americium dioxide and europium oxide mixture. This was of course a publication when we sent to the inorganic chemistry. There were some queries by the reviewer. They said that carry out the studies with the simulated spent nuclear fuel. So we carried out some studies taking 5% europium spiked into this, and also 10% europium spiking. And this mixture, this XRD pattern is given for the 10% SSNP, that is the simulated spent nuclear fuel. You see this spectra for before leaching as well as after leaching, and see here this europium oxide peak was seen, and after leaching it was removed, and then you are having mostly the uranium dioxide spectra. So suggesting that dissolution of uranium dioxide was very, very poor, and this was shown by the XRD pattern of the europium. Then we have tried to carry out some speciation of the dissolved europium complex in the ionic liquid. We have taken this dry ionic liquid, wet ionic liquid, and we have carried out extraction, the normal solvent extraction, taking a water and ionic liquid phase, the TTA extract we got. And we have carried out this excitation as well as the emission because europium is there, and we have seen that this decay constants for the dry FTIL, wet FTIL as well as the extract, they are more or less same. That means around more than 2.2 millisecond was the lifetime. They are suggesting that there was the inner coordination sphere, that is no water is present, and the species of the type europium TTA4-, which was suggested, which was confirmed by exams as well as the DFT studies. So basically the species which is formed in case of the europium dissolution with the ionic liquid is europium TTA4-. So to conclude, the solvent extraction of actinides by ionic liquid has been suggested by many researchers, and they have proposed that this as a prelude to a possible fuel cycle application. However, there are question marks because there are many researchers, they don't believe in this. They don't consider basically the ionic liquids really as green because there is a lot of loss of the ionic liquid into the aqueous phase because of the cation exchange mechanism operating in some cases. And the better option in view of this is the direct dissolution or the selective dissolution. Selective dissolution is like europium is dissolved and americium is not dissolved, so that is a selective dissolution. So that actually helps in the separation of this mixture of oxides, and subsequently the electrochemical deposition can be done, resulting in a process which are free from aqueous processing. So this way you can avoid. Now what is the advantage of the ionic liquids? Because they have the wide electrochemical windows, and that is how you can operate this electrodeposition without much problem. Though non-specific ionic liquids like butane-based HBET-TF2N are found promising, the proton-releasing ligands such as DEPA and STTA can also be used in an ionic liquid for the dissolution purpose, which we have demonstrated. UO3 dissolution was possible by the DEPA ionic liquid system, and a unique pre-concentration mechanism appeared quite promising. But UO2 dissolution was not possible by the DEPA, but as mentioned by Bruce Meyer's group, you can have a whole oxidation, that is VO2 can be oxidized to UO3, that is the step they have used. So if you have that step introduced, then you can have dissolution of UO2 as well. Electrodeposition was possible to complete the cycle, and the extractant can be recycled. STTA ionic liquid system was quite interesting for the americium europium suppression studies. The solid oxide structure was playing an important part in the dissolution reactions, and based on this difference in the structures of these oxides, even the rare earth oxide suppression can be made possible. Many difficult separations so that the intra-group separation of lanthanides and actinides can be attempted by this method. Thank you for your attention.
Thank you, Dr. Mahapatra. So after an exhaustive presentation on ionic liquids, though we have very less time, so we can take one or two questions.
A very interesting lecture. I have one or two small questions. So basically, what I have understood is that two important criteria. One is the lattice energy, that is, you have given some figure of about 10,000 kilojoules, but if it is more than that, it is difficult to dissolve. And the other is the water content. Now, in one of the previous work of the previous author, they have shown that zirconium and cerium, they come along with actinide.
Yes.
They don't move with actinide. So I guess this must be because of the higher lattice energy.
Yes.
Because cerium has a tendency for tetravalency, and those things we have higher type.
MO2 type.
Zirconium also, I think, we will.
Yes.
So that is something one has to look into, because we need actinide only. We don't need those things. Your second suggestion that perhaps we can also do intra-group lanthanide separation, I think that is more difficult because the lattice energy is going to be more or less similar. So one has to fine-tune your extractant or the liquid which can have that intra-group separation. So that will be a difficult thing. Last question which I want to understand is that you have done extensive work by showing the role of water for the TTS system, wherein you say that keto-enol will shift toward the enol which helps in the complexation. But what is that you have not mentioned anything about the role of water in the HDHP system. Though you have said, I did the centrifuging and the lighter phase pump, where the uranium phosphoric acid complex at the top.
Yes.
Whether any water is present there, or whether you are trying to add water and understand the behavior, and what
That is the unique selling point of that. Yeah, water you cannot put there because it is a octyl ionic liquid, C8 nim. So octyl group is there. It is more hydrophobic. So water tolerance is much less there. So you cannot add water to that. Whereas C4 nim is a lower, softer alkyl chain. So the water tolerance is more. So you can have more. You can saturate with water more there. So it was. That's why we have not studied the water part there. But as you said, it's lanthanide intragroup separation. We have already, I am not presented here, but we have carried out a lot of studies, extensive studies we have carried out. We are filing a patent actually. So adjacent lanthanides we can separate with a very high separation factor as 500. So this is a success actually, and we have shown it, we have demonstrated it. So we are filing a patent.
But how with the same lattice energy you are able to do it? I mean, there is some other trick also involved there?
Yeah, that I will discuss privately.
Okay, we'll stop here. We'll go to the next speaker. Before that, I have the present duty of giving a moment to Dr. P.K. Mahapatra.